So last week, the largest battery electric aircraft ever flew and took off from New York. Now, Heart Aerospace's X1 is a beautiful aircraft. It has a 106-foot wingspan, more than 25,000 pounds at takeoff, and 4 electric motors that deliver more than a megawatt of power. It flew for 27 minutes, and Heart says the electricity that it used during this flight was $5. That's incredible from an economics viewpoint. That's the headline. That's the tagline that we've seen all across TikTok and every aviation design website. But I think everyone's missing a more important and interesting number. And that number is 0, because during that flight, the mass of the X1's energy store changed by essentially nothing. Now that seems trivial, but it's a fact that could eventually change the way that we design, the way that we engineer, the way that we operate aircraft from a global standpoint, and it changes everything. A conventional airliner takes off carrying tons and sometimes tens of tons of fuel, and as it flies, it burns that fuel, so the aircraft gradually gets lighter. But an electric aircraft doesn't do this. A discharged battery weighs, for practical aircraft engineering purposes, exactly the same as what a charged battery weighs. And then suddenly the design assumption that we've lived with throughout modern commercial aviation changes. Think about this. Think about the landing. Think about the kinetic energy the aircraft has to get rid of, that 1/2 mass times velocity squared. So all else equal, more landing mass means more energy to dissipate through the complexity of tires, the complexity of the braking system, aerostructure that has to deal with this. That does not simply mean electric aircraft need enormous brakes. Imagine carrying that weight for the entirety of the flight. Transport aircraft brakes already have to survive extraordinary maximum energy rejected takeoff tests. But this changes the optimization. The aircraft no longer gets the structural benefit of having burned tons of fuel before every normal landing. And then it gets even more interesting beyond this. Airliners commonly store fuel inside the wings. We've seen this within bladders that expand and contract. And that isn't just convenient packaging, it's engineering. The weight of the fuel distributed through the wing partially opposes the aerodynamic lift that bends the wing upwards. This is a huge design component of how wings are done. So a US transport aircraft structural study explicitly notes that moving fuel into the fuselage removes that wing bending relief. So where do you put several tons of batteries? And obviously you put them now predominantly into the fuselage, but then you've changed the structural load, the L over D, and the distribution of how the aircraft designs and behaves.